Hi, and welcome to Complex Numbers Day 2. Alright, we're going to solve these little equations very easily for x. So what I do is I add 1. So x equals 1. And then for b, I'm going to subtract 1 and subtract 1. So x equals -1. And then for c, I'm going to add 1 and add 1. So I have x squared equals 1. And then we know we have to take the square root, so x is equal to plus or minus 1. We can't forget our plus or minus. Or we can solve that by factoring it, saying x plus 1 and x minus 1 equals 0. Because it is the difference of two perfect squares, so x equals -1 and x equals +1. For b, subtract 1, x squared equals -1. And up to this point, you've been told that if you get that, there's nothing you can do, there's no real solution, and you're done. But that's not the case. We can still take the square root of both sides, and we will still get an answer. In this case, we'll get plus or minus I, because the square root of -1 is equal to I. Somebody along the way decided that we needed a way to deal with these negative numbers when we're taking square roots. And this is what happens when your parabola, for example, does not cross the x-axis. You still have roots, but they're what we call imaginary roots. You can't see them. It doesn't actually touch the x-axis, but there is a solution. And so they used I for imaginary because it couldn't be seen on the axis like we normally do with an x and a y. But it doesn't mean that they don't exist. It's not like your imaginary friends from when you guys were little. Something that's not in here that I need to add is an I clock. And this is going to be 1 I, -1, -I. On the outside, it's I to the 0, I to the first, I to the second, I to the third. This little clock is very helpful when we're dealing with powers of I. And as we get to that, I will show you in some of the problems, and I'll also do some more examples with you in class. But that's something you're going to want to learn and memorize. So I know it's kind of fast with this introduction of I, but it is what it is. We will spend more time in class on it. So I is an imaginary number, and when you put a real part with it, you have a plus or minus bi. A is the real part of the number, and the bi is the imaginary part. So when we combine like terms, we combine real parts and we combine imaginary parts. So here, this is just simply an addition problem. And since there's no number out in front of the parentheses, it's just 3 plus 4i plus 7 minus 20i. I'm just going to combine like terms. I have a 3 and a 7, which is 10, and then a 4 and a negative 20, because 4i and negative 20i is going to be a negative 16i. And that's all I need to do with that. Just combine like terms. You kind of treat I like a variable. When we subtract, we have 3 plus 4a, and then I'm going to distribute that negative, does that make sense? So minus 7 plus 20i, so 3 and negative 7 is negative 4, positive 4i, positive 20i is positive 24i. multiplication with complex numbers is a little bit different. You can use the box method if you want. Or you can just multiply. So I have 1 minus 2i plus 2i. So when I multiply 1 times the negative 2, and I get negative 2i, and 2i times 1, so 1 times 2 is 2. And then my last terms, I get negative 4, and I times I is I squared. And when we go back to that little clock, I have 1i, negative 1, negative I on the outside, and I to the 0, I to the first, I to the second, I to the third. You can see that I to the second is really negative 1. So that really changes and becomes a negative 1. So I have 1, and then when I combine these two terms, negative 2i and positive 2i, they cancel each other out. And then negative 4 times negative 1 becomes plus 4. So my answer is really 5. So multiplication with complex numbers, we're going to verify that negative 1 plus 2i and negative 1 minus 2i are solutions. And before we learned that if we substitute the values into the equation and we get a 0, that meant it was a solution because there was no remainder. So that's what we're going to do at this point. So I'm going to take negative 1 plus 2i, cut it into x squared, plus 2 times negative 1 plus 2i plus 5 equals 0. So let's write negative 1 plus 2i times negative 1 plus 2i. Then I need to distribute that 2. So minus 2 plus 4i plus 5 equals 0. And when I multiply here, negative 1 times negative 1 will give me 1 minus 2i, and then another minus 2i, and then a plus 4i squared minus 2 plus 4i plus 5 equals 0. So I squared becomes a negative 1. So this whole term becomes negative 4. So if I collect my terms, I have a 1, a negative 4, negative 2, and positive 5. So I have 6 and a negative 6, which is 0, negative 2i, negative 2i, a positive 4i, which is another 0. So 0 equals 0 works out. So negative 1 plus 2i is indeed a 0. Now I need to do the same thing with the other root. And I'm actually going to let you try that one. I'm just going to substitute in negative 1 minus 2i squared plus 2 times negative 1 minus 2i plus 5 equals 0. And then show me that that really works. That's really all there is for today's lesson, but I really wanted to show you this graph here. This, when we graph in the complex plane, we didn't really talk about it in the notes. In the complex plane, this is still x, and this is what we call yi. And if you want to think about it when I was talking about a complex number, a plus bi, this is really your a part, and this is really the I part. So if I take letter A, 5 plus 2i, and I want to plot it on the graph, I'm actually going to plot the point 5, 2. I'm going to go over 5 and then up to I. So this is A. And that's how you would do that. And I think that was all the extra stuff I wanted to show you today. All right. We'll discuss more in class.